Hello, everybody. This is Aaron Schwartz, one of the secondary math specialists with Montgomery County Public Schools. This screencast is called Building the Perfect Rectangle, and it's actually the third in a sequence of videos about developing procedures around quadratics. If you haven't viewed Building the Perfect Square or Building the Not So Perfect Square, it may be helpful to view those screencasts before looking at this one. In Unit 4, Topic 2, the students learn to model quadratic relationships with expressions by exploring patterns and connecting to area. Quadratics can be modeled using diagrams of rectangles and squares. The algorithm for factoring can be understood and derived from such diagrams. Factoring is an emphasized concept in the Common Core State Standards, appearing at least twice. It appears in Reasoning with Equations, where students are expected to solve quadratic equations by factoring as well as other methods. It also appears in Interpreting Functions, where students are supposed to use the process of factoring to show zeros or other information about the graph. This is particularly important. The way the standard is written, it's not that we look at the graph to reveal the standard form. It's that we're actually going to use the factored form to examine what the aspects of the graph should be. Some helpful skills that students have mastered at this point include that algebraic expressions can be used as models of patterns. This appears in IM and Math 8, and it appears earlier in Algebra 1. So you can see that I've changed the title from Building a Square to Building a Rectangle. But we're going to start out with some of the same ideas. We're not going to build a perfect square, but we are going to build a rectangle from x squared plus 4x plus 3. We're going to have some of the same procedures. We're going to leave the two sides open on the x squared tile, and we're going to describe how the x tiles and the unit tiles are arranged. One of the key things that is unique about this approach is that we can actually combine the learning of factoring and the double distributive property into one lesson experience. They don't have to be taught as two separate and two unrelated skills. So let's go ahead and see what this looks like. We start with our x squared and we expand out. Students may expand out as they've done when they were completing the square and realize there's an issue here, we're missing a square. And students may even say, oh, this is supposed to be the square of x plus 2 minus 1. And they would be correct in that. But we have to emphasize we're not worried about the square, we want the rectangle. So again, we'll start with our x squared. We'll expand out. But this time, the only way to get the rectangle is to only expand the other pieces in one direction. What we want students to observe is that we actually have two dimensions to this rectangle, to this area diagram. We have one whose side length is an x tile and one unit tile. We also have a side length of one x tile and 3 unit tiles. So that we have that the square of x plus 4x plus 3 is the same as a rectangle with the dimensions x plus 3 by the dimension x plus 1. Students may actually notice certain things at this point. They may notice that 3 times 1 is 3 and that 3 plus 1 is 4. And that's a really critical thing for students to observe. But we need to make sure that that works in all scenarios and then synthesize it into a procedure. So we're going to build another rectangle. We're going to build the rectangle from x squared plus 5x plus 6. We're going to use the same rules. We start with our x tile. We'll expand it out. And we'll see that we get this nice rectangle. Our rectangle has a dimension of x tiles across the bottom and 2 unit tiles. And along the side, it has a length of 1 x tile and 3 unit tiles. So the area of x squared plus 5x plus 6 can be represented by a rectangle whose dimensions are x plus 2 by x plus 3. And again, students may immediately notice 2 times 3 is 6 and 2 plus 3 is 5. This is a critical understanding that we now want to synthesize. So in a classroom, we might ask students to do this several times, not just the two that we recorded in the screencast, but a couple different trinomials. We may ask students to observe this with different sets of trinomials and see if their conclusions are the same regardless of the trinomials with which they engage. For right now, we're going to synthesize this learning into a table. Students have already engaged with the x squared plus 4x plus 3 and the x squared plus 5x plus 6. Let's say we've also asked them to engage with x squared plus 6x plus 8 and x squared plus 7x plus 10. And they've gotten their areas as products of length and width. We want them to make some observations. So we may ask them what they notice, and we may need to focus their question to be what do they notice about the linear term, the coefficient of the linear term, and the constants in each of the factors. They may immediately notice that 1 plus 3 is 4, 2 plus 3 is 5, 2 plus 4 is 6, 2 plus 5 is 7. If they're noticing this, then they're picking up on one of the key patterns. We also want to ask them about the connection to the constant in the trinomial. When doing this, we want to clue them in that there is a connection that they should observe and describe. In this case, 1 times 3 is 3, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10. So the constants in each of the two factors, the length and width, have a connection both to the coefficient of a linear term and to the constant in the trinomial. In fact, we can now generate a rule. For a quadratic, if x squared plus bx plus c is equal to x plus m times x plus n, then b is equal to the sum of m and n, and c is equal to the product of m and n. This is only true for a quadratic with a lead coefficient of 1, but we'll get to other quadratics in a minute. We can now use the algebraic manipulation to verify what we just observed. We can represent the double distributive in a number of ways to verify what students have discovered. Students have now figured out a way to both factor and distribute without actually going through the algorithm. Now we want those observations to serve as an understanding of the algorithm. Typically, we do this by looking at the distributive property. We start with the product of x plus 3 and x plus 1. We distribute that x plus 3 to each of the terms in the expression x plus 1. We distribute again, and then we group like terms, and we come up with the square of x plus 4x plus 3. But there's other ways to accomplish this, and there may even be other ways that are more accessible to students. Let's take a look at columns. We've typically learned about multiplication in columns, and we typically learned about it when multiplying out two-digit numbers. But actually, column multiplication works for any base of numbers, not just base 10. It works for base 2, works for base 7. It even works for base x. Just as we would, we'll start with our lower right-hand corner. We'll do 3 times 1 to get 3, and 3 times x to get 3x. Just as we would if this were multiplying numbers in base 10, we'll put in a 0 in the ones column below our plus 3. And we'll do x times 1 and x times x, so that we get x squared plus 1x plus 0. And when we add those expressions together, x squared plus 4x plus 3. But there's another way. Because at the beginning of this, students engaged with algebra tiles. So what if there was a way to use the algebra tiles to tie into both factoring and distributing? And the key is thinking about the arrangement of the length times the width. And that's where factor boxes come in. When we think about factor boxes, they really arrange the same way as those algebra tiles. We're going to have a square tile. We're going to have two different segments of linear X tiles, and we're going to have a units tile. So when we look at that blue, or the X squared, X times X, X squared. 1 times X, 1X. X times plus 3, 3x, and 1 times 3 plus 3. And when we group our green or our linear terms, x squared plus 4x plus 3. And we've done our distributive property. And what's great is this is actually going to work in reverse. But you know, all of the examples we've looked at have only worked with a lead coefficient of 1. To better develop student understanding, we have to explore quadratics in which a is not equal to 1. So now we're going to build a rectangle from 2x squared plus 13x plus 15. We're going to start with our 2x squared tiles, just as we always have. Now we run into a situation that's a little bit more complicated, because we don't know how to arrange that 15. That 15 could be 3 by 5. It could be an array of 5 by 3. It could even be an array of 1 by 15 or 15 by 1. We just don't know. So we're going to move on from those, and we're going to start by looking at the x's. We got to think about this 13x. This 13x is going to be interesting because we're going to have to divide it up into 3 groups. We're going to need 2 groups that are equal and 1 group that might be equal. We don't know. The groups could be 1x, 1x, and 11x, 2x, 2x, and 9x, 3, 3, and 7. For the sake of the video, we're just going to go to the correct answer. In this case, we're going to have a group of 3x's and 2 groups of 5x's, or just 10x. We now know that we have an array of 3 by 5. So we have our 15 and we have our rectangle. So there's some things that we want students to observe now that they've gone through this experience, and hopefully several other examples where the lead coefficient is not 1. In this case, let's go ahead and break up the expression. 2x squared plus 10x plus 3x plus 15. What we really want students to do is to make some observations about the 10 and the 3 and the 2 and the 15. And we want them to do this for several quadratics where the lead coefficient is not 1. One of the conclusions that we hope that they would draw is that the lead coefficient times the constant is equal to the product of the 2 linear coefficients. 2 times 15 is 30, 10 times 3 is 30. And this one piece is the critical information that we need to do all of the factoring. We can now modify the rule that we had before and say that for a quadratic, ax squared plus bx plus c, if b is equal to the sum of m plus n, then actually it's not c equal to m times n. It's actually a times c equals m times n. And from here, we can introduce the idea of factoring by grouping. We can observe that our 2 different halves of our expression can both be factored. 2x squared plus 10x can both be factored by 2x, and 3x plus 15 can both be factored by 3. At this point, once we've taken out our common factor, students might observe that we have x plus 5 in both of those. This is the reverse of the distributive property. 2x plus 3 times x plus 5. But a lot of students may gravitate towards the factor boxes, so let's take a look at those. Again, whenever we have factor boxes, what we're really representing is the number of squares, the m and the n number of x pieces, and the constant c arranged as an array. We're going to remember our rule, and that's where we'll start. So let's factor 15x squared plus 11x plus 2. We know we need to do 15 times 2. That's 30. So we want to list out the factors of 30 so that we know how to break up that 11x. 1 plus 30 is 31, so that's not going to work. 2 times 15 is 30, that's not going to work. Excuse me, 2 plus 15 is 17, that won't work. 3 plus 10 is 13, that's not going to work. But 5 plus 6, that's 11, that's the pair that's going to work. And so we have 15x squared plus 5x plus 6x plus 2. We can do our factor by grouping and factor out the common factor in each term. And there we go. But what about those factoring boxes? What about factoring using that mechanism? Well, we have to start out the same way, and we still have to find out what two sums of m and n are going to equal b, and what product of m and n is going to be the product of a and c. So we'll still have to do that factoring part. But now we can arrange, instead of a massive diagram with 15x squared tiles, we can just write 15x squared, 5x, 6x, and 2. And we can look across the rows and columns and identify common factors. The common factor across the row 15x squared plus 5x is 5x. The common factor of 6x and positive 2 is plus 2. The common factor of 15x squared and 6x is 3x. And the common factor of 5x and 2 is 1. And now we actually can check across by multiplying out using the factor boxes. 3x times 5x is 15x squared. 3x times 2 is 6x. 1 times 5x is 5x, and 1 times 2 is 2. So we know we have the right factors. 5x plus 2 times 3x plus 1. And we're done. We've now learned how to factor and use the distributive property simultaneously and with the same mechanisms. I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below.